This video is on PES, which stands for photoelectron spectroscopy. So it's a big word, or two words, I guess, but it's actually an idea that is a fairly simple idea once it's explained. And it's a combination of two things. It's a combination of our understanding of ionization energy, which we've just been talking about, and electron configurations. So 1s2, 2s2, and so on and so forth. So this idea combines those two things graphically to produce something called a PES spectrum. So before we get into that, I do want to discuss or review what ionization energy is. It's abbreviated IE, and ionization energy is the energy that's needed to remove an electron from a neutral atom. So we're talking about how much energy does it require to remove an electron, okay? And we learned the trends for ionization energy and what atoms require more ionization energy to remove than others, and all of that stuff. So as a quick reminder, I'll go ahead and fill that in. Ionization energy increases as you move up a group, and that's because the electrons are getting closer and closer to the nucleus. And it increases to the right as you move across a period, and that's because from a very simplistic point of view, that this side of the table are the elements who want to gain electrons. They don't want to lose electrons, and so to remove an electron costs a huge amount of energy. So that's the general trend for ionization energy. Now, one thing that maybe we didn't emphasize quite so much before, and this is the biggest idea in PES, is that the ionization energy of a core electron, okay, remember cores are your inner electrons, is much, much greater than the ionization energy of a valence electron, okay? And so that is probably the biggest underlying idea in PES, is that it is so much harder to take the core electrons than the valence. And think about why. Because the core electrons are located closer to the nucleus, and therefore they're experiencing that stronger pull from the nucleus than the valence are. So it's much easier to remove a valence electron than a core electron. And this is a big idea when it comes to this understanding of PES. So what exactly is a PES spectrum? So I define it as it's a graphical combination of an element's ionization energy and its electron configuration. Okay, that's not like the totally true definition, but it's my definition, and I think it's a good one because this idea encompasses these two very big ideas in chemistry, which is that of ionization energy and that of electron configurations. Okay, so what does a PES look like? Well, there's different kinds of them, but for the most part, they all resemble something that kind of looks like this. It's a graph, and it has peaks, okay? And these peaks represent something. So before we get to that, let's talk about the axes of this graph, okay? So we have the y-axis, and on the y-axis for all PES graphs is going to be the number of electrons. And on the x-axis is something called the binding energy, which actually is just another name for ionization energy. And think about why. Ionization energy means the energy needed to remove an electron. So binding energy is kind of how tightly those electrons are held to the nucleus. So it's kind of the same thing, okay? Most of the time you'll see binding energy, sometimes you'll just see energy, sometimes you'll see ionization energy on the x-axis. Okay, so let's go back to saying, or actually before that, and then the third thing that you'll notice is that the x-axis kind of seems to be reversed. Look at it. It starts at a binding energy of 100 and it gets smaller, right? Isn't that not normal? Isn't most of the time the, zeros over here and the x-axis increases? So this is a little bit different. Most PES graphs look like this. And I'll show you why. So again, back to this big point, which kind of electron takes more energy to remove, valence or core? Core, by a big amount. So in this graph, right, where the ionization energy is on the x-axis, here are your electrons that take more energy to remove, right? 100 is greater than 5 or 1. So these are the beginning of your core electrons, and over here are your valence, right? How did I know that? Again, because this takes way more energy to remove than this, according to my graph. So that must make the valence down here. So then all we do is we start with our electron configurations, and we say, okay, what electrons would require the most energy to remove? Well, they would be the 1s. And what I'm going to say is that, assuming that this continues, which it surely does, that 1s orbital is going to have 2 electrons in it. Okay, so this kind of part of the graph must mean 2 electrons. So that's the 1s with 2 electrons in it. Then I notice that my energy decreases by quite a bit. So then the next orbital I would encounter would be the 2s. Okay, notice it's the same height as the 1s, corresponding also to 2 electrons. So what comes after 2s? Then it would be 2p. Okay, notice this time, it's definitely not 2 electrons, and it's probably about 3 times as tall, right? So this represents 6 electrons, and we know that the 2p holds 6, so this should be making sense to us. Following the 2p comes the 3s. It is in fact, this almost, because of I hand drew this, the same height as the 1s and the 2s, meaning this holds 2 electrons. And then after the 3s comes the 3p. Now notice this is not representing 2, okay? And it's not quite double. Double would probably be up here somewhere. So this must be representing 3 electrons. So then this would be 3p3. So looking at a PES, right, we now know whoever this thing is. Oops, what did we say? 3p what? 3. We now know that this thing has an identification. And so if I go to my chart and I figure out who this is, 3p3, it's phosphorus. So this is the PES spectrum of phosphorus, okay? Something kind of cool to think about. We know that phosphorus has 5 valence electrons, okay, because of our shortcut that we can count. It has 15 electrons total, so that must mean that 10 are core. Well, look at this. So the 1s, the 2s, and the 2p are all the core. 6 in the 2p, 2 in the 2s, 2 in the 1s, so that's 10. And then these, I should have changed my color. Oh well, are valence. Right, remember the definition for valence: highest energy level, level 3. And sure enough, 1, 2, 3, 4, 5 valence for phosphorus. So the kind of neat thing about PES is that it's also almost like a fingerprint. Every element has a different PES spectrum because they have a different number of electrons, okay, in, when they are an atom. So we can figure out who an element is if we have a PES spectrum to look at. It was kind of cool. I do want to bring your attention to the fact that there can be a couple different types of PES. These are less common. But you actually can have one that starts like we would think a graph would, small to big energy, but that just means you have to flip your brain around. You always have to think, where are the electrons that are really hard to remove? In this case, they're down here. So in this case, this is the core, and this is going to be the valence, and we're kind of going the opposite way, right? So I hope you understand that this is not the 1s. This is the 1s. This time, okay, and it's because the axis is flipped the other way. So again, 1s2, look, this time they even put lines on there for you. So then this is 2s2, this must be, 2p6, this is 3s2, and then this is 3p1. So this is actually also phosphorus, right? Nope, I just lied, I'm sorry, it's not phosphorus, 3p1. This is aluminum, okay, so this is aluminum's PES spectrum, but it's kind of reversed only because the axis was reversed. So keep that in mind. This is less common, but you could see it. Okay, oops. Oh gosh. And then the other one is way less common, but it's kind of like a double graph. They're like stacked on top of each other. I'm not really sure why they do this, although it does do a pretty decent job of showing you valence and core. So in this case, again, all you have to do is watch your x-axis. So here's my low energy, here's my higher energy, right? 10 to 100, somewhere up in here. So this is going to be your core. And it's even telling you that there's 2 electrons. So this is the 1s with 2 electrons. And then, of course, the next one is the one with the highest energy. So this is the 2s, 2, and this would be the 2p, 4. And so, again, we should be able to identify this graph as oxygen based on just our understanding of electron configuration. Okay. One interesting thing I want to show you real quick is, let's do something. Let's do oxygen again. So I'm going to say that black on my graph is going to be oxygen. So the oxygen atom. So O. Okay. So let's say I'm just going to put some numbers in here, 100, 10, and 1. We'll go like normal. So if I was going to do oxygen's configuration, 1s2 is where we start. So that would be up here somewhere with the core. So that's the, I'm not going to label it. I'm just going to say it. That's the 1s2. And then skipping a pretty decent amount of energy, this would be the 2s2. And then oxygen is 2p4. So a column that's about double. And that would be oxygen's PES spectrum. Now, I want to think about the oxygen ion. So when oxygen forms an ion, it forms O-2. Okay. And so that means that oxygen has gained 2 electrons. So I want to think about what its PES spectrum would look like. Well, it's still oxygen, so the energies are going to be the same. And so I still have a 1s2. Oops. I still have a 2s2. Right. But this time I wouldn't have 2p4, I'd have 2p6. So the third peak for oxygen minus 2 would look something like that. And that's how you could differentiate between O and O minus 2 if they were on the same graph. So something kind of neat to think about. The other thing I would like to show you real quick is how would this look different if instead this were, I don't know, let's say lithium. So lithium's in the same period as oxygen. It's in period 2, but lithium's is a 1s2, 2s1. Okay, so it's definitely going to not have as many peaks. It doesn't have a 2p peak, but I also want to talk about something. See, because I've changed atoms now, the ionization energy for lithium is going to be different. So if we go all the way back up to the top where we talked about ionization energy, here's oxygen and here's lithium. Okay, so lithium's ionization energy is much smaller than oxygen's. So that means on my PES, there's going to be a shift. So we just said that it's going to be easier to take lithium's 1s electron because its ionization energy is smaller. So where oxygen's 1s electron was up here, maybe lithium's is somewhere here, because while there's still 2 of them, right, I should have made my peak a little bit taller, the peak height is the same, give or take, but the ionization energy is different because it takes less energy, right? So see, this is less energy than this, so this is a little bit confusing. So then 1s2, and then I would just need a 2s1. So the 2s should be less energy than oxygen's 2s. So, I mean, I'm guessing, maybe it could be in between these peaks. It could even be all the way down here. I don't know. I'm just guessing at this point. And it's going to be half as tall because it's only representing 1. Okay, so one thing you have to think about when you're comparing different species on a PES is, does the number of electrons change? Okay, if so, your peak height will change. which that was the first case. That was when I did the black and the red, the O and the O minus 2. But then the second question you have to answer is, will your ionization energy change? Okay, and if so, then the peaks are shifted on your graph to represent that change in ionization energy. So that's PES, and like I said, basically it's a combination of two ideas. It's a graphical combination of ionization energy and electron configuration.